Okay, I start again. Okay. Hey everyone. Thanks again for this nice introduction. Today I'm going to talk about our ICLE papers. When can we use flatness to guarantee adversarial robustness? And I think a good chunk will also be about when we can't and when it's unfortunately not as useful as we would like it to have. And the first thing is, I'm just going to start very basic. I mean, probably most of you have seen this slide roughly a million times. So, what is an adversarial example? So, we take an image, in this case of a panda, we add some adversarially crafted noise, which is then done via FGSM or PGD or some other gradient ascent attack on the input space, and add it, and suddenly the network predicts it's a gibbon. Now, there has been a lot of research in that direction, but still an open problem how we can fix this. And our idea was, because flatness has been shown to be quite useful for generalization, can it also help to analyze whether we can solve adversarial robustness? Now, what is flatness? It's a very, very old hypothesis already introduced by Hochreiter and Schmidhuber in 1995. And the idea is very simple. So these are large regions in the weight space where the loss with regarding to the weights stays constant. That's in a flat region. And if it wiggles a lot or changes a lot, it's called sharp. Very simple. The intuition is that if we now um, have a little noise somewhere, the network will stay the same and we will have better generalization. So empirically and actually provably this works. So here in this plot taken from this basically groundwork on relative sharpness by Henning Petzka, Michael Kampe, and Lina, which is also here in the talk, where you can see that if you measure flatness or relative flatness or some other version of it and compare to the generalization gap, you see that it decreases. So the flatter it is, the better the generalization gap is. Now, you can prove this, and empirically, it also correlates quite well. Then, what is generalization? Typically, people by now kind of think it's just good test performance, which is mostly wrong. So, it is the difference between the error on the overall distribution minus the empirical distribution. That is how well it generalizes to unseen data. Now, what here Petscat showed is that you can decompose this into a global property and a local property, where this global property is not too interesting for us, but there is this local property called feature robustness, and this is based on flatness, which means that generalization depends on how flat the loss surface is. Now, how to measure flatness can be decomposed in two sets. So there's empirical and analytical. For the empirical case, very, very simple. You just perturb your weight space with some random perturbations and take the average. And it gives you a notion of how much is your loss going to change with respect to these changes. And the worst case, you essentially take a adversarial step in the weight space and see how much it changes in the worst case. And this gives you then a notion of what they call worst case flatness. Given that this is very expensive and not as amenable to theoretical investigation as we would like to have for what we are planning to do, there's also an analytical version to solve this, here called relative flatness, introduced by uh, Petska et al. And essentially, every analytical flatness measure more or less depends on the spectrum of the Hessian matrix with respect to the loss and the weights. In this case, we look only at the penultimate layer of the cross entropy loss, and why this is possible, I will argue later. But on certain networks, it really nicely decomposes that you just have to consider the classifier and the feature extractor separately. More details later. Okay, then there's also empirical evidence that when you measure this average case flatness, there is indeed a strong correlation between robustness. So here on the left, on the y-axis, you see the loss on these adversarial examples. Here, there are like various adversarially trained models. I mean, I think in total over 20. And then here you have this average case flatness, what I showed earlier, where you just sample weights in the neighborhood and evaluate the flatness as well as the loss. And you can see that it nicely correlates. Okay. Now, when we now want to connect adversarial robustness to flatness, which is a bit of a problem because flatness is measured in the weight space. So we And the adversarial examples live in the input space, which means we now need to connect this geometry from the weight space to the input space such that we can give guarantees on how much the input space can change, such that we will get yeah, robustness. Okay. The main idea is quite simple, and to make this actually theoretical sound, a bit of work is necessary. I will go into detail later, but the changes in the input somehow translates to changes in the weights. And if you take this very easy or approximate derivation, right? You start with your function and it has weights, and then you put some noise on the input, do some arithmetic, and in the end you will see that you can write it essentially as a perturbed weight matrix times the input. And if it's now flat, that loss, or if it has like a high flatness, then the loss will roughly stay the same. And the intuition is that if the loss is somewhat similar, we would hope that the prediction is similar. And later I will show that this is not always the case. And this is the first limitation that we will see, that flatness cannot make any statements. Okay, the next connection to adversarial robustness is that if you look at the standard definition of an adversarial example, you just check whether in a certain neighborhood there are perturbations such that the prediction flips. This is the standard definition. This has been used roughly since 2014 and changed ever so slightly depending on what the paper wanted to show. So, but given that we are working on the loss and not necessarily on the specific prediction, we also need a loss-based definition, which more or less looks like this. We say we have a epsilon delta adversarial example if the input changes by delta, and we also only have a change in epsilon. I mean, it's essentially already a smoothness condition, and if you write it like this, it becomes somewhat clear that you would expect a nice connection there. If you now want to formalize also robustness in the sense that adversarial robustness usually means that there is no prediction flip, which means in our case, okay, there is within a certain neighborhood just not a sufficiently high loss change depending on the perturbation. And there you see that there is immediately a additional assumption, meaning this only works if the loss is less than ln2. And why is that? ln2 means essentially that your ground truth is predicted with at least 0.5 confidence. And the problem is that if we have a look now at all these three histograms where we plot, just in an example, the probability distribution of the output layer, you can see that here for this middle one and this right one, the cross entropy loss is the same, but the prediction is different. And this can only happen if the loss initially for the predicted label is less than is bigger than ln2, because then the margins don't work out anymore. Which already then shows the first limitation of flatness for making statements about adversarial robustness is as soon as for your specific sample that you want to make a guarantee, the loss is bigger than ln2, you cannot make any statements already. Okay, then for the rest of the talk, let's say we have only considered samples where the loss is less than ln2, so where this definition holds. Then we can connect relative sharpness to adversarial robustness. The main idea is that we will measure the relative flatness in the very last layer, so the classifier. And with that, we're gonna give bounds in the also in the penultimate layer in the feature space. How much perturbations do we allow in the input, also in the feature space, which then gives you these nice balls, these L2 balls, where you can guarantee that there will not be a certain loss increase. And if the loss is also less than ln2, there will not be a prediction flip, meaning the model is adversarially robust in that region. Then we will port this back to the input space, more or less through the pre-image of the feature extractor, where then the guarantee is not as big anymore, because the pre-image can do weird stuff, in particular can morph it arbitrarily. So in the end, the bound can be significantly smaller than what we had in feature space. Next, I want to argue why is this even possible that we decompose the network into a classifier and a feature extractor to make a statement of the input space by only measuring the geometry of the weight space in the very last layer. So first of all, we want to understand what is this flatness actually made of, this relative flatness. So for a given feature extractor and a classifier, which applies to softmax. Here, softmax is very important that we consider this. This is the basic definition of the relative sharpness measure. If you now compute this trace of the Hessian with simple arithmetic, you get this formula. And I mean, this is mostly what you already see in undergrad because this is just the Hessian of logistic regression for multi-class laws. Which you then you can see that it mostly consists of three main terms. It's a weight magnitude. Makes sense that this is here. So if your weight matrix in the last layer is not as big, you would expect that the model is also not sensitive. Then the next thing is also that the feature scale is somehow small. Then you would also expect that your model is somewhat stable. And here, very important is confidence term. And one thing to note is that this confidence is computed via softmax, meaning as we increase the logits, this thing in any of the classes, this term will rapidly go to zero. And this also means is that the geometry is mostly dominated by confidence. I think for people that worked on information geometry and other stuff, this is not so surprising. I mean, it's just softmax and cross entropy. But here it has also very interesting implications for guaranteeing adversarial robustness on standard neural networks. Now, why is the last layer sufficient, given that we only measure it in the curvature in the last layer? So we only consider here affine ReLU networks, and intuitively, the curvature should propagate very cleanly through the network, because the only thing that induces any curvature is the loss. I mean, if you have ReLU activations, there's not much curvature going on. You have only affine transformations. They have no second derivative, so also nothing there, which means we can basically just look at the recurrence equation for computing the Hessians. And here you see there is this HL, which then for computing the Hessian of the previous feature vector, you just use the one of the next layer and so forth, and you get this nice recurrence equation where the seed of curvature, that's how we call it, is just given by the loss. Meaning if we can make this go to zero, also this becomes very flat, then this also is incredibly flat, like obviously only locally, but this is the argument why we can just look at the very last layer to make statements about the input layer, because the curvature just is, as soon as it's close to zero, essentially everywhere the same, namely zero. Okay. With that, we already then come to the proof idea. And from there on, that's intuitively quite simple. Technically, it's a bit annoying because you have like very big terms and Taylor decomposition and such. But the basic idea is that you go from the input space to the feature space. Use typical assumptions like Lipschitz continuity of the feature extractor, such that these small changes in the inputs induce a somewhat controlled feature change. And we also measure this empirically. This seems to be the case. So adversarial examples don't result in an incredibly high suddenly a feature representation change. So it's still somewhat constrained. It's mostly angular actually, which makes sense. Then the next step is we rewrite these feature perturbations in as an equivalent perturbation of the last layer weights, what I sketched like a few slides earlier, which then is also not as hand-wavy as before, but you can make this properly. Then use a Taylor decomposition to bound the loss, and then you have like a second order and a third order term. The second order term then just is your relative flatness measure. This falls out nicely. And with that, you can then bound the loss, increase depending on the perturbation, and finally, you just solve for the radius. Like for the initial input perturbation, you can just solve for this via Cardano's formula, which gets ugly, but still it's manageable. It's like big formula, but conceptually very simple. Then we get two main theoretical results. Essentially, what we see here, free Taylor expansion, is this proposition one, meaning we can bound this perturbation or the loss increase in the perturbation depending on the curvature or this relative flatness measure. And as you can see, if this now goes to zero, also the loss increase will decrease, yet it's still dominated by a local Lipschitz constant. And then you solve for the error, for the perturbation. And here again, you see that as expected, the curvature is in the denominator, meaning if we get this to zero, the certified radius is going to increase. Yet, obviously, it needs to be bounded because there's still this problem that we have, first of all, still this local Lipschitz constant. And also, we will not be able to change the input geometry, meaning if points are already close at the somewhat natural decision boundary, we will not be able to fix it. There's this typical reconstruction construction for a counterexample for a universally adversarial classifier. Okay. Any questions up till here? Because then we go to the experiments.
Just go to experiments because for the recording we don't ask
Good.
questions.
Makes sense. Now, the goal is here, first want to validate that our theory that we derived is also sensible, so that the curvature properly propagates to the input, and not only very locally, but we can observe it in a bit of in a broader area. And also test the theoretical insights that we had from proposition 2 and 1, meaning if we now have truly a flatter network, we would expect that the loss increase is limited in that local neighborhood. And finally, we show that not only sharpness does not give us too big like a very big radius, but it can only be deceiving if you're not aware of what it's actually measuring. Here, the setup is the architectures that we tested in the papers, like REST 18, so all the common confnets and only with batch norm layer. Datasets, Cypher 10, Cypher 100, basic standard protocol, nothing fancy, but here we don't adversarially train yet. Now, how to control this sharpness? This is a bit of a initially seemed like a hard problem, how we can deal with this, because if we want to, let's say, have a very nice plot in the sense of the flatter network gets, the higher our certified radius becomes, we have this problem that if we retrain over and over again, there may be also many other factors which influence the robustness, meaning the robustness of the feature extractor, which is not what we essentially want to measure here. But looking at this, and the theory is that we can basically just scale the last layer weight because this confidence term is going to pull this to zero very quickly, and then we can control very nicely how the sharpness of the whole network is going to change. And we have this advantage that the feature extractor is the same for all the comparisons that we do. Okay, then here we test now these scaled networks. To test our hypothesis, we generate adversarial examples and evaluate on the trajectory. Here, one thing to mention is that given modern or the neural networks that we look at are not robust, we also use a very, very weak attack to even see how that changes and how robust we get. So we have 25 steps. Epsilon is also really small and also very small step size. Note that we use the PGD L2 attack because our bound just works for L2. And I mean, technically you can also upper bound it then, but we just stuck with this here. Okay, and the first thing we want to just take one sample, we draft adversarial examples, and then measure how the loss changes. And here the legend shows you the different scaling factors. And the more we scale, you see that on this trajectory, the loss becomes flatter and flatter, and very nicely as expected. And you get per sample like these basins. So you have all these samples around them. There's like a basin of where the model is flat, or in this case, even robust to our notion of robustness. Then next, we also measure the loss increase. And if you look at the left figure, it's always almost clear that this is what's supposed to happen. So the flatter the network becomes, or the more we scale, the smaller the loss increase is. Essentially justifying what proposition 2 showed, proposition 1. Also, what's interesting is that per sample, the bound that we can give is very dependent on this local Lipschitz constant. So these takeoff points, which we call, like if you really scale the last layer to infinity, mm, is different for all other for essentially every sample. So meaning that every sample has its own local Bézier in which it resides. And finally, so this is not predicted by our theory, but this will more or less make people happy that believe that flatness can have a more global um, impact or statement for the loss surface. Namely, we measure here the relative sharpness at 0, so before we attack, and then we show that and measure the Bézier width. So how long does it take until the loss just explodes? And what we can see is that we have a nice negative correlation. So the flatter the network is at 0, the bigger the Bézier is, independent on how we scale it post hoc. Okay. So we also then train networks adversarially to check what is the effect of adversarial training for flatness and other parts of the neural network. And essentially we find it's exactly the same. All what happens is that the Bézier width becomes significantly bigger. And this is more or less known that adversarial training mostly um, increases the margins and also um, the local Lipschitz constant around each sample. So yeah, essentially we have 20 times bigger Béziers, but except that exactly the same behavior. Now, finally, we turn to the problem that flatness can be deceiving. So here we go back to normally trained networks. We generate adversarial samples with L infinity, standard setup, 10 steps, epsilon 8 over 225, and also the alpha is quite standard. If now flatness were a sufficient measure for robustness, we would hope to see this. So if we then can use flatness to check whether this is an adversarial example or not, we would like to see this. So loss increases, but also then sharpness, so the network becomes somewhat uncertain or whatsoever. But we don't, and we see this. So as the attack progresses, the network becomes less and less flat. And this little increase here, this is more or less the loss increase. Like this is roughly where our bound works still. And here, initially we called this the uncanny valley, and there is still some uncanny part to it, but it's if you look at the relative sharpness measure and you see how it propagates through the whole network, that at, this just is an area where the model is incredibly confident. And this is also what adversarial attacks do. They create these very high confidence wrong predictions, which means is that we have now a almost plateau where all the predictions are wrong. The network is incredibly flat, kind of violating this idea that flatness can help us to make statements about robustness in almost every situation. But note that this is essentially covered by this ln loss less than ln2 condition. And we can also see that it's really a broad in the sense of it's not just one point, but in that vicinity there are many of these wrong predictions. And the basic experimental setup is you generate adversarial examples, you sample in the neighborhood and just see how the loss and the sharpness changes. And you see that for a significant amount of distance to the basic, like measured here in L infinity, you see that the network still remains relatively flat. So it's not exactly zero, but it's still very flat. Okay, then we turn to the next problem, namely, if you were now to naively optimize for adversarial robustness by using this relative sharpness measure, you're also in a bit of a weird situation because by making your network very flat and you achieve this, then what's likely going to happen is you just do gradient masking because at the same time when the hashness is going to vanish, also your gradient is going to vanish, and your adversarial example or adversarial attack is just not working anymore, although the network is susceptible. So what we show here on the right is that we measure the robust test accuracy versus how sharp the network is. But instead of attacking the network directly, like the scaled networks, we attack the unscaled networks and then use these points that we found to evaluate the scaled networks. And we see it's similarly non-robust. So this really does not have anything global, but just in a very local neighborhood, you can you can see this. One thing that you can avoid or postpone a bit is the prediction flip, but it's also like almost local. So then the question becomes, can we somehow fix this? Like, because it's so baked in into these neural architectures that you have cross entropy and softmax. So then what you want to check is, okay, maybe a different sharpness measure would help. And the answer is it doesn't really fix it. So what you can show is quite easily is that your sharpness measure somehow needs to combat this exponential decay, and meaning your sharpness measure needs to be more than polynomial at least in the weight space and in the Hessian spectrum, such that your sharpness measure will not vanish as soon as your network becomes confident. So this is also not that easy of fix. Then can we try different losses? Are there some? And maybe there are some, but we don't have them yet. Because what we can show is that under a very technical condition that essentially all modern losses that we use fulfill, the the Hessian still will vanish as soon as the network becomes confident in one of the classes, making again sharpness measures not necessarily useful for making statements about the global robustness of neural networks. And the main problem appears to be the softmax function and how it's computed. Okay, this is unfortunately the current state for guaranteeing adversarial robustness using sharpness. So to more or less answer the initial question, when can we use flatness or sharpness to guarantee adversarial robustness? So we can not do it as soon as the loss exceeds ln2. Then even if we can do it, it's somehow small and very limited and mostly dominated by the local Lipschitz constant. And if we go beyond that, it's unfortunately almost deceiving to measure flatness and make statements about global properties. Okay, good. Thanks a lot for listening. That is essentially the current state that what we have, and now I'm looking forward to your questions.